with. So, if you can recall, we were talking about different types of amplifying medium, is not it? We talked about solid state gaseous medium or semiconductor based medium, liquid media, etc. Of course, their configurations are slightly different depending upon how we excite that medium. Okay. Excitation is essential, so is to pump the ground level atoms or ground level electrons to the upper level, right. And then transitions, electronic transitions, right, or molecular transitions helps us to achieve population inversion, 3 level system or 4 level systems. So, those some of these media, they have such different transitions, useful transitions for laser, for light amplification. Okay. Inverted population in right, population inversion is possible, and that allows amplification. And so, pumping can be electrical pumping, right, in input pump energy can be electrical in input, right. In case of a semiconductor material, we provided electrical input to right, bias the right semiconductor material, right, with right, forward bias is good enough. Electrical input is also useful for generating the discharges in gases, right. So, most of the gaseous molecules, they will get excited through the discharge, right, process. So, electrical input to produce the discharge, and that discharge is basically is right, carries the gaseous molecules to the upper energy, right, other excited energy levels, and then the process. So, electrical input may be in that sense, right, useful for semiconductor materials, semiconductor media or gaseous media, right, gaseous media. And optical input are also possible. Optical input, you can excite the medium with an another right input, pump right, optical input to excite, and that is useful for solid state crystals. Okay. Solid state right, amplifying media crystals such as neodymium YAG, right. We so okay, as simple as ruby, which is chromium doped sapphire, or neodymium doped yttrium aluminum garnet, or okay, this is ND-YAG, it is known as ND-YAG laser also. Okay. Or it may be for there are many such crystals available. I am talking about, I am just writing down few of them. Okay. And titanium sapphire. Okay. Okay, titanium sapphire. So, Ti 3 plus ion doped, okay, or chromium or neodymium, etc., provide solid state such crystals, and they are pumped by optical right input. So, it can be a flash lamp, okay, to produce to provide energy, but when we give flash lamp input, the spectra, flash lamp output spectra is quite broad, while as per the energy transitions, etc., you must have seen that those absorption lines are quite well defined. A particular wavelength, it will absorb efficiently, not all the wavelengths it will absorb. Okay. So, some of the light from the flash lamp will go waste in heating the medium, etc., indirectly. It will not provide us the efficient right output. So, they may use sometimes optical input is either using a flash lamp or using diode lasers itself, right. They are tuned to a particular wavelength matching with the absorption band of the optical crystal, this thing, which is efficiently right pump, diode laser based pumping. Okay. So, the pump will be optical in nature, but diode laser output is used to pump another laser medium, lasing medium. Okay. So, that is optical pumping, etc. So, that is related to pump energy. The media, as already I told you, it can be right, semiconductor or gaseous or solid state, right. So, this is amplification medium, and amplification medium is we already discussed. So, but there are many, so right, and we last the one which we discussed was titanium sapphire medium. So, this medium has the characteristics, it has many vibronic bands, okay, and that allows basically right, tunable laser output, okay, tunable laser output, okay, it is not here, but it has many right vibronic bands, upper pumping level as well as the ground level, okay. Okay, and you when you excite this medium with a green light, because titanium sapphire crystal has a very good absorption around green light, okay, absorption around green light. So, now green light, let us say 500 nanometer or 532 nanometer. You know what is 532 nanometer we can obtain from where we can obtain? Second harmonic of neodymium YAG laser corresponds to this wavelength. So, I can use neodymium YAG laser to pump titanium sapphire laser, in fact, okay, to pump it efficiently. Then the pumping will carry the excitation, then internal transitions, and then lasing action, and then internal transitions back to the ground level. And this is the depending upon which energy state is right getting excited, how it is transition takes place, the output wavelength varies from 650 to 1100 nanometer, okay, for a titanium sapphire laser, okay. Maybe tomorrow, if I'll bring this crystal, how it looks like, you will see tomorrow, we will see that, okay. So, this is tunable. So, this provides, so in case of a neodymium YAG laser or a ruby laser, etc., if you see the spectral characteristics, okay, with respect to the output intensity from the laser, you will see that the spectral characteristics is quite narrow. So, this will be of the order of less than nanometer order spectral width, okay, in terms of wavelength. This is about Nd:YAG laser or ND3 plus or ruby laser, okay, chromium ruby lasers, etc. They have narrow, of course, the center wavelength, fundamental wavelength may be different. For neodymium YAG it is 1064 nanometer, for ruby laser it is 694 nanometer, but the spectral width of the distribution of right intensity distribution in wavelength is quite narrow. But if you see titanium sapphire laser, okay, titanium sapphire laser over here with the right intensity or right output power lambda, it is quite broad, it is quite broad, okay, approximately as I told you 650 to 1100 nanometer, quite broad, few right 100, 200, 300 nanometer broad. If you consider I was talking about dye lasers, right, dye laser also has a broad band spectrum, but not as broad as this much, okay, 30 to 40 nanometer width, okay. Okay, so this laser, so you may argue that initially we talked about laser means having a monochromatic right light source, having only one frequency, one wavelength, of course, right. Then how can you treat titanium sapphire output, right, output as a laser, okay, you may argue like this. However, because of this vibronic bands, it has such a broad gain bandwidth, but by using some technique we can tune a particular laser wavelength to oscillate, okay. So, I can tune this laser to oscillate at a wavelength of 800 nanometer, okay, and it will be narrow band 800 narrow band laser output from titanium sapphire laser. And if I change some conditions, then the wavelength will get tuned to some other output wavelength within the gain bandwidth of from 650 to 1100 nanometer, okay. Of course, as you go in the as you go to extremes 650 to 1100 nanometer, here two extremes, the gain may be very small. So, output power may be not be so high. In the center wavelength is approximately 800 nanometer. Okay. So, approximately around 800 nanometer, the gain is very large. It is not symmetric, okay. Remember, it is, although I have shown it as symmetric, actually the emission and emission characteristics, if you see, it is slightly, right, 800 nanometer, slightly away from center, okay, towards right left. So, this is what are the different types of media which will result which provides us amplification at other wavelength than the pump wavelength, the light, and that amplified output is also undergoing some feedback, right. The feedback in all this, right, lasing media, gaseous, semiconductor. So, here here liquid also, right, liquid media, etc. They are all based on optical mirrors, right, mirrors are deposited. So, feedback is using mirror. Okay. In case of electromagnetic waves which are away from the visible or near infrared or UV range, right, much different spectral region, the feedback need not be using mirror, it will be using, right, reflections, using impedance matching, R, C, etc. will play the role. Okay. It is same thing, it is happening here, but it is physical mirror which is providing this feedback. Okay. So, this is in general the laser system will have this pump input, amplifier, amplification medium and a feedback that determines the whole laser cavity, okay, cavity configurations. And what we write, and the related one more threshold condition for laser action to really start, okay, just simply by providing some pump input we will not get the laser output as it is, because the cavity within this medium where the light is oscillating, etc., has certain loss, encounters some losses. Okay. The losses may be at the mirror end, the losses may be because of the scattering in the crystal or semiconductor material, the losses may be due to some other species present in that cavity which may absorb some light, etc. Hence, basically if you consider laser cavity with an amplifying medium. So, in an amplifying medium there will be some gain, correct, gain associated with this. Gain means a particular wavelength will amplify, okay, as we it is an amplifier for that purpose, right, it is a gain. Of course, pump is here, gain is here, related this, and this is a feedback. So, having a reflectivity, let us say R1, R2. Okay. What I will do, just nothing changes, I will write in terms of gain, I will write in terms of gamma gain, okay, in terms of red. Okay. Pump I will represent it with, let us see, pump. Okay. So, I want to distinguish, do not think that pump is getting amplified, it is not pump, right, it is amplifying medium which emits some other wavelength, and that gets undergoes amplification. Okay, remember. Okay. So, it is, so this medium emits some right, amplifying medium emits some light and it undergoes, right, to and fro, right, feedback. But every end when it is undergoing to and fro at this point R1, it experiences some reflection while some transmission as well, correct, and at the R2 also some reflection corresponding to the reflectivity and some transmission, okay, etc. And there is again gamma, right, and there is a loss as well. Okay. The loss is due to some absorption, some scattering in the within this cavity, etc. So, let us say the losses are represented by losses, okay, loss alpha, okay, that is loss, okay, alpha is the loss within the cavity. So, the laser output, let us say the reflectivity over here is slightly less, transmission is little more as compared to R1, then of course, the laser output can be from this side or from this side also, depending upon the reflectivity etcetera, right, some transmission may take place. So, this is now every round trip there is a gain, there is a loss and there are reflection losses, correct. These are reflection losses, gain and cavity losses determines the overall right amplification of this line. So, the net gain, okay, net gain in such right cavity is determined by so round trip corresponds to 2 times of length, right, 2L. So, if the length of the cavity is let us say L, okay. So, gain is exponent of 2 times gamma, right, at a particular frequency or lambda nu, right, into L, right, gain coefficient is gamma per centimeter, okay, gain coefficient gamma is unit is let us say per centimeter and L is the length in centimeter. So, this is the net gain, this gain plus right, this is into exponent of minus 2 alpha corresponds to nu to L. This is the loss, right, factor which is coming into R1 R2, right, reflectivity, okay. This will determine the total gain, okay. This determines the total gain and at threshold where after right at a particular value where net gain is 1, right, beyond which the laser output starts, okay. At threshold net gain is 1, beyond which the laser output starts, okay. So, so threshold gain coefficient, right. So, this gamma, right, at threshold can right will determine. So, gamma nu at threshold when it is given by based on this equation 1 by alpha alpha okay, plus 1 by 2 L natural log of 1 by R1 R2, okay, will determine this. So, generally it is something like this, okay. The example is little vague, but it will give you some idea. Let us say there is a dam, water dam, okay. Now, rain is constantly falling, okay, constantly rain is coming in. The water dam has some leakage also, is not it? There will be some water which will get seeped in, right, in the earth crust etcetera, it will water will go. So, there are some losses, water is coming in, it is some part of the water is getting lost due to the seepage, okay. But some part of the water is getting accumulated and it slowly the height of the water in the dam, right, high water, right, increases and but still the dam size is such that the amplification is increasing its out height, some leakage is also taking place and rain water is constantly coming, but still the water overflow is not observed till it reaches a particular threshold, beyond which whatever amount of rain comes will go out, right. So, amplification and gain will compromise, will compensate with each other and some there will be some outflow, okay. So, that outflow will be the laser. So, within the laser cavity when you start pumping, let us say pump energy is small enough to produce means, of course, when pump is there, amplification will come into excitation, amplification comes into picture, but there will be some losses as well. So, losses are there within the cavity, there are some losses, there is some gain also, but if that gain is not more than the losses which it experiences, laser output is not seen. Okay. So, what we will see in terms of threshold, in terms of how the threshold will look like, it is something like, if this is the pump input power, okay, pump input, and this is the laser output. Okay. Initially, when pump is exciting the medium, medium will start amplifying various at different wavelengths. It may have little broadband output depending upon its gain characteristics, etc. All this excited, this whatever light is getting emitted, amplified light will start oscillating in the cavity. Now, the cavity decides which particular modes will oscillate, right, depending upon the longitudinal modes. Only particular modes which are forming a standing wave will start oscillating, other waves will get suppressed because they will get lost due to losses. So, finally, what we will see at a particular frequency, if the laser gain amplifying medium has a narrow spectral width, up to certain input power you will not see much of the laser output, it is a broadband, but beyond certain power, where beyond crosses the threshold, the output rises. So, this may be a threshold level beyond which pump input will result in a better output. Of course, efficiency will depend upon the amplification, etc. It's and this will determine the laser output characteristics. Okay. So, till the threshold is reached, we will see that the spectral bandwidth of the output will be quite broad depending upon many modes which are oscillating, but as soon as the beyond threshold, only a few modes which satisfies this standing wave configuration will only oscillate, and that is why they will give you the output which is, and which results in the narrow spectral mode output characteristics. Okay. So, little more complex, if I describe in a complex way. So, you see laser cavity with length L, medium is, let us assume simplified, cavity, and so which are the modes which will oscillate in this cavity modes which can oscillate. Okay. So, there will be frequencies components which will oscillate, okay, and which are those modes? They will be, the separation will be decided by C by 2L, correct, C by 2L, and this nu 1, nu 2, nu 3, nu 4, all of them can oscillate. Okay. Now, this medium, that is a medium, that is a medium which provides, which has a gain, Now, that gain, so there is a medium which has a gain something like this, let us assume. It can oscillate at within a wavelength range, particular wavelength range. Okay. It can provide amplification, not oscillate, but it can provide amplification flight. Okay. Now, out of this spectral bandwidth matching with this mode selection by the resonator, this is a resonator characteristics, correct, a resonator characteristic, this determines Of course, some part of the refractive index over here, this is with small and small l, will determine the little different mode spacing, because this will be L1 plus L2 plus 2 NL, etc., right. Refractive index will play the role corresponding to, here refractive index is 1, here it is 1, but here it is n. So, the mode spacing may be slightly different, okay. You can estimate, okay, this. So, it will be L2 times L1 plus L2 plus NL, correct. L1 is this part length, this is L2 length, correct. This will determine, okay. Now, this may be slightly, but now you can see the gain is this red color line spectra, while the modes which can oscillate are these modes, okay. And as the pumping starts increasing, okay, pumping starts increasing, the gain starts increasing, okay, gain starts increasing, gain based on the gain coefficient, okay. This is the gain coefficient, gain curve, okay, gain coefficient values, right. And for the total gain which comes into picture due to this will be now particular frequencies. These are the frequencies which will oscillate, not all this, right. So, you will get maybe correct, something like this it will come. So, you will see the laser output with such frequencies nu 1, nu 2, nu 3, nu 4, nu 5, and whichever crosses a threshold limit of this cavity will, you will see some such outputs, okay. And of course, depending upon some other ideas, you can ensure that the losses with all other frequencies will be maximum to allow only one particular mode to oscillate and provide, okay, that is also possible. So, now this is basically the laser output which determines. So, if there is no laser output, if it is only amplification, you will see the broadband spectra from that amplifying medium, but if you allow feedback and resonator cavity, you will see with beyond threshold particular modes which will oscillate, narrow band modes, optical modes, okay. So, this is what is right, will end up with, right, laser output. And as I told you, this modes also can be suppressed, okay. Only one particular mode of interest can be tuned also, okay. We will see, it depends upon the gain bandwidth, etc. We may, whatever I have shown you as a broadband gainwidth, if the laser medium has a narrow band gainwidth, you will see only one particular mode which will oscillate, isn't it. So, that is the one. So, this is one aspect, okay, related to many of such modes which can oscillate based on this cavity. That is another right. Now, how will you select these modes? How will you select these modes, okay, which modes you want it to oscillate. So, if the gain bandwidth is more, you can even tune the laser, as I told you, okay. So, the selection is possible with the help of some right resonator cavity configuration, okay, or right cavity, right, configurations will decide what type of modes. If I am just simply using straight this right launch this cavity and allow pumping, amplification and the laser output here, this is pump, etc. You will see that the mode spacing between, depending upon the gain medium, mode spacing is decided based on this length of the cavity, etc., as we discussed just now, and the laser output will have multiple modes, okay. So, depending upon the gain medium, and the spacing between two consecutive modes will be determined by this, right, optical characteristics of this resonator, etc. However, if I want to select a particular mode which will oscillate, let us say it is a widely the broadband amplifying medium, it has many modes which can oscillate, okay, not very narrow like this 3 modes only, or it may have multiple modes which can oscillate. Then in that case what we can do, one configuration is we can use, okay, let us say very simplified way that I will use a prism, okay, inside the cavity. It can be outside the cavity also, okay, possible. So, if I use a prism, now there are, let us say 3 modes which are oscillating, okay, nu1, nu2, nu3, okay, 3, or it may be multiple also, as I told you, it depends upon gain medium, there may be 4, 5 also modes. Now, 1 nu1, nu2, nu3, if they are oscillating in this cavity, and let us say 1, this goes here, then it goes here, and there is a mirror, okay, this side. So, this is mirror R, one high reflection mirror, let us assume high reflection, okay. This is mirror with some transmission, okay, some transmission. So, the output high reflection means no losses on this side, okay, 1 minus R is 0, okay. So, but theoretically of course, there will be some losses, but let us, and the transmission is from here, okay. Now, as you know, nu1, nu2, nu3 have different frequencies, okay, and so wavelengths are different, of course, right, small difference depending upon the mode spacing. So, one frequency will oscillate like this, the other right frequency may, so let us say this is nu1, okay, this is nu1, nu2, let us say we represent it with blue, this thing, okay, it has different frequency, so different refraction angle, correct, different refraction angle through prism, right, prism will disperse the light depending upon the wavelength and frequency. So, now this is nu2, you are clear, is it okay? It is very exaggerated, it will not be so far apart dispersion, but just to know, okay. The third frequency is, let us say nu3, okay, nu3 is okay, say they will be oscillating along the same line, just to give you color difference. So, they are oscillating and it has intermediate some other, right, wavelength. So, it is nu3. Now, this mirror, okay, helps us in selecting a particular mode, particular light optical wavelength which will go back in the cavity, while all others will get lost. If this is 90 degree over, exactly this is 90 degree over here, right, 90 degree, mirror is 90 degree to this, what will happen? Only that light which is reflecting back will reflect back in the cavity, correct, will reflect back in this cavity, correct, while all other light this will reflect somewhere this way or other way, this way, correct, it will not return back to the cavity. Losses, we have introduced losses in the cavity, okay. Although cavity allows all the 3 modes to oscillate, but we introduce losses corresponds to nu1 and nu3. So, the light photons which are coming back in the cavity as only nu2. So, the amplification will be taken care by only nu2, correct, because amplification comes into picture when photon comes into picture. Populated in population inversion is there, photon comes, it will excite, stimulated emission will be because of the photon coming inside. So, nu2 will induce stimulated emission to emit one more nu2, 2 nu2 will again induce 2 more, right, 4, 8 multipliers, while nu1 and nu3 can oscillate, but losses are more. So, number of photons coming back will be so less, they will not be able to extract the energy from the excited states as much as nu 2 can extract, is it okay? So, indirectly now if I change the angle of this mirror such a way that now this right mirror is tuned to let us say 90° to this right violet 90°, then only nu 1 will oscillate, right. Losses for nu 2 and nu 3 are much more. So, nu 2 will right oscillate and provide things, is it okay. So, what are you doing is you are tuning the laser wavelength corresponds to nu 1 or nu 2 or nu 3 or many more. If the gain bandwidth is large, if the gain bandwidth of the laser material itself is very small, not much of such many modes will not be there. Of course, there will be there because in terms of frequency they will be very nearer, okay, but not as many. Okay. So, this is what is the tuning. However, prism is provides this type of selection through dispersion, but the prism is a coarse tuning element, okay, coarse, because this angle is not very wide spread. Okay. So, to allow single mode oscillations with this needs very large cavity. Okay. The prism should be placed in the this mirror can be placed far away, so that you can distinguish nearby all angular, right. So, it becomes much complex, etc., but of course, you understood the technique. So, to tune the laser, right, we may use not the prism, dispersion material prism, okay, dispersion, okay, characters prism we are using, correct. We can use diffraction as the approach, okay, diffraction grating. So, we can use to tune the laser length, we can use diffraction, okay, by using a diffraction grating. So, diffraction grating is right, it is something like right some structure with a particular periodical right structure, okay. This is a periodical structure with a reflection with a now the light which is coming in at a particular right normal alpha incidence, okay, alpha is the incidence angle, the light will get diffracted, okay. Now, because of this periodical structure with grating this diffraction grating period lambda etc., right this. So, m lambda is to this grating period sine of plus beta, okay. Bragg's equation very similar to the Bragg's equation, okay, over here, and m is the order, okay, 0th order, first order, second order this. So, if you see this equation, okay, so depending upon the wavelength, the alpha input angle remaining the same for lambda 1, lambda 2, lambda 3, right. Wavelength is different, grating periods is constant, physical constant, m is let us say constant first order, alpha is constant, input angle incidence angle is alpha, then beta only the reflection angle will change, correct. So, the corresponding to lambda 1 this equation will get satisfied for beta 1, okay, lambda 2 beta 2, lambda 3 beta 3 let us say, right. That means, the light with lambda 1 wavelength will diffract at an angle beta 1, while light with lambda 2 will diffract at an angle beta 2, correct, and the third one may be at an angle beta 3. Okay, you understood, no? Right. That means now this angles will help us to determine which particular right feedback can be given. So, if I draw this now configuration in our laser cavity, okay, which is Littmann configuration, okay. It is because the scientist Littmann had found out this approach, okay. So, okay, this is an amplifying medium. Now, there is a grating structure, okay, and there is a okay, depending upon lambda 1, lambda 2, lambda 3, the diffraction angles are different, correct. Now, if I put mirror, if I use a mirror, correct, which is 90 degree to, let us say this, then only this particular wavelength will be able to oscillate, okay. And this is the first order. See, now if you go back to your physics class, what you had learnt, in fact, in you would have learnt diffraction grating, but at that time you would not have realized what it is, what is, okay, we would have plotted like this, okay, with this is lambda dispersion, okay, and this is the reflection right, reflection from the grating, okay, intensity, the light which is getting reflected, okay. What you will see when 0th order, okay, m equal to 0, you will see that it is only all the wavelengths, not, this is not wavelength, spectral dispersion, no, this represents spectral dispersion. Basically all the wavelengths will be at one line, the intensity will be, as you go to, this is m equal to 0 mode, if it is m equal to 1, so it is some, actually it is like this, okay, much wider. So, m equal to 1 and m equal to -1 has slightly broader spectrum than this, but intensity decreases. M equal to 2 second order has much broader spectrum than this, but the intensity further decreases. Okay. This sinc function you would have learnt in your some practical physics experiment somewhere, but without realizing, okay, teacher is asking, we are doing this experiments. But then basically the one of the applications of this, right, aspect is, so 0th order output does not have any diffraction, okay, no diffraction, right. So, I should represent not in terms of, see this one, it should be in terms of theta, right, this diffraction angle basically, okay, will be less. So, 0th order output will have no diffraction. So, all the output, whether all the 3 lights, okay, all will have the same angle output, okay. If it is first order diffraction, what we use, it will have a some diffraction coming into picture, right. And if I try to use second order, the diffraction will be even larger. Only problem is the feedback reduces because the intensity reduces. So, first order, 0th order has a larger intensity of the light, which will come out as an output. Okay. This is a reflector which reflects only part of this, right, diffracted light in the first order diffraction. So, m equal to 1 diffraction will be used to provide the feedback to the cavity. Okay. right. So, this is internal, it is used, grating is used inside the cavity, but as the losses are large inside the cavity, sometimes the cavity becomes much more heavy, losses are there. Because of this, see, we are using only reflection for the small part of the light is getting reflected back, losses are large as far as the cavity gain is concerned. So, sometimes we use external cavity, similar configurations, but first let laser oscillate, okay, and this R will be partially reflecting, okay. This is high reflection, this is partially reflecting, partially transmitting, large let us say 30%, 50% reflector, 50% transmitter or whatever. So, the threshold is of course quite high, but then we provide the grating structure over here and provide the output will be here, the diffracted output will be used and mirror, external cavity mirror, external another mirror will be used, cavity mirror, to provide the feedback to this cavity, okay. And the laser output is obtained from the 0th order. So, this is 0th order without any, right, 0th order, no. So, whatever incidence angle alpha, right, corresponding based on the equation, it will be decided this beta without any dispersion, diffraction, okay. That is 0th order, and then first order, second order we do not use, first order to provide feedback. So, first order m equal to 1 mode to provide the feedback, 0th order to get the output, okay. Okay, laser is used. So, this is external cavity right configuration for tuning the laser, okay, for a particular wavelength. Now, you can understand titanium sapphire crystal I can put here, it will emit broad band gain width, but by using this configuration I can select which wavelength it should operate, is it okay. I can put semiconductor lacing material here, and using external cavity grating structure like this, I can provide the feedback to get the tunable laser output at this thing. Is it okay? So, with this here I am stopping. Tomorrow we will talk about this, everything whatever we are talking, we will talk about right spectral characteristics of the laser, pulse means basically pulsed output lasers also, and the beam characteristic of the laser, okay. And then after we will go to the detectors, by what are the detectors that we use for our applications, okay. Okay. Thank you very much.